Hello everyone, welcome to my video about rubidium spectroscopy. When I did my research on the topic as preparation for a lab course, I thought that there were no videos that explained it perfectly, and that is why I am giving it a shot. So now first of an introduction. Why do we talk about rubidium? Why do we use rubidium? Rubidium is one of the most important atoms in modern quantum optics. It is used in laser cooling, atomic clocks, quantum sensing, and photonic quantum technologies. One reason is that rubidium has accessible optical transitions at around 780 and 795 nanometers, which can be driven using a simple diode laser. In this video, we will explore how rubidium interacts with laser light, why we observe so many resonance peaks instead of just one, and how we can reveal the full fine and hyperfine structure using saturated absorption spectroscopy. Let us begin with the simplest possible picture. If we shine laser light on an atom, we expect a single electronic transition. The atom absorbs a photon when the laser frequency matches the resonance frequency of the transition from the ground state G to the excited state E, using bracket notation in this case. This energy difference should be exactly, and I mean exactly by that, delta E equals h times f, where h is Planck's constant and f is the frequency of the photon. In this simple two-level model, we would see only one single absorption line when we scan the laser frequency over resonance. However, real atoms are more complicated than that. Before we talk about hyperfine structure, we first have to understand the fine structure, which comes from spin-orbit coupling. The electron in the atom has orbital angular momentum L and spin angular momentum S. These combine to the total electronic angular momentum J, which is just L plus S. Because the electron moves in the electric field of the nucleus, in its rest frame it experiences a magnetic field. This leads to a coupling between its orbital motion and its spin, called spin-orbit coupling, which is, as hinted at by the word rest frame, a relativistic effect. This leads to the fact that states with the same orbital quantum number L, but different total angular momentum J, have slightly different energies. The states are thus not degenerate anymore. For rubidium, the relevant excited states are the 5p states. Due to spin-orbit coupling, they split into 5p 1 half with J equals 1 half and 5p 3 halves with J equals 3 half. These give rise to the two famous D lines of rubidium. The D1 line, which is the transition of 5s1 half to 5p1 half at around 795 nanometers, and the D2 line, which is the transition from 5s1 half to 5p3 halves at around 780 nanometers. So even before we consider the hyperfine structure, our excited state, which was previously just one line, is already split into at least two different fine structure levels. But now we go even deeper. We have to talk about the hyperfine structure, which is a coupling between the electron and the nucleus. Even each of those fine structure levels, which we have previously talked about, such as 5s1 half or 5p3 halves, is not a single state. They are further split by the hyperfine interaction between the electron and the nucleus. The electron's total angular momentum J is associated with a magnetic moment. This magnetic moment creates a small magnetic field at the position of the nucleus. The nuclear spin and nuclear magnetic moment play huge roles in this case. Rubidium has two naturally abundant isotopes: rubidium 85 with a nuclear spin I equals 5 halves, and rubidium 87 with a nuclear spin of 3 halves. Non-zero nuclear spin means that the nucleus also carries a magnetic dipole moment. The magnetic dipole moment of the nucleus interacts with the magnetic field produced by the electron's angular momentum, and this coupling leads to an additional splitting of the atomic levels into hyperfine levels. Because of this interaction, it is convenient to define the total angular momentum, which is F equals I plus J. The quantum number F can take values from the absolute value of I minus J to I plus J. Each possible value of F corresponds to a distinct hyperfine level, slightly different energy. Now we look at an example, the ground state hyperfine structure in rubidium. For the ground state 5s 1 half, where j equals 1 half, in rubidium 87 with I equals 3 halves, we get f equals 1 and f equals 2. Why is that? Well, the absolute value of I minus j is the absolute value of 3 halves minus 1 half, which is 1. And I plus j is 3 halves plus 1 half is 2. The splitting between these levels is about 6.8 gigahertz. In rubidium 85, with I equals 5 halves, we get f equals 2 and f equals 3. The reasoning behind it is exactly the same as before. The splitting is about 3 gigahertz in this case. Similar hyperfine splittings also occur for the excited states like 5p 1 half and 5p 3 halves. These gigahertz scale splittings are huge compared to the natural line width, which is only in the order of a few megahertz. So instead of a single transition from G to E, from the ground state to the excited state, we actually have many allowed transitions in the form of F transitions to F prime between the hyperfine sublevels of the ground and excited fine structure states. However, something important to note, not all of those transitions to F prime are allowed. Electric dipole selection rules require that the total angular momentum must satisfy delta F equals 0 or plus minus 1, with the exception that the transition from F equals 0 to F prime equals 0 are forbidden. The reasons for that go beyond the scope of this video. Here we have a pretty nice picture showing us the different hyperfine levels of rubidium. We can see our ground state in this case has f equals 1 and f equals 2 in the case of rubidium 87. And when we look at a transition from this state, from the f equals 2 state, it can only go to the f prime equals 1 state, to the f prime equals 2 state, or to the f prime equals 3 state. So when we do the experiment, we are going to see 3 hyperfine peaks for this case. On the right hand side, you can also see it for rubidium 85, where the main difference are the numbers for the hyperfine levels and the difference between them. So you can see here the frequency difference between the f prime equals 2 state and the f prime equals 3 state are 270 megahertz in this range. So now let's talk about the actual measurement. What are we actually measuring? So to observe these transitions, we perform a simple experiment. We shine a tunable laser through a rubidium vapor cell and measure the transmitted intensity, or the absorbed intensity. We continuously scan the laser frequency across the D-line region and record how much light comes out of the other side of the cell. So what would we like to see? Well, if the atoms were at rest and there were no broadening mechanisms, we would just see several narrow absorption dips, one for each allowed hyperfine transitions. But this is not what we actually see right here. In reality, when we just send a single beam through the cell and look at the transmission, we typically see only one broad absorption feature with no clear individual lines. The reason for that is the Doppler effect, due to thermal motion of the atoms. In this picture, you can see the setup of the experiment. The laser comes through here. You don't really have to mind the polarizer. It goes through the rubidium vapor cell and into the photodiode. This would be what you see at on the screen. This is the absorption spectrum, and you can see those dips. They are not the hyperfine dips, not at all. They are way larger. They're in the range of a few hundred megahertz. So, what is the Doppler effect, and how do we get rid of it? Well, the Doppler broadening is why the structure is washed out. We first have to talk about thermal velocity distribution. At room temperature, atoms in the vapor cell move with a thermal distribution of velocities. Along the laser beam direction, their velocities follow the one-dimensional Maxwell-Boltzmann distribution. So the atoms move. What does this change? Well, an atom moving with velocity v along the beam direction sees the laser frequency shifted due to the Doppler effect, which is, for small velocities, delta omega equals minus omega 0 times the speed of the atom divided by c. So this is how much the observed frequency is different to the actual laser frequency. Omega 0 is the atomic resonance frequency in the rest frame of the atom. So atoms moving towards the laser see a higher frequency, which is also called a blue shift, and atoms moving away from the laser see a lower frequency, which is called a red shift. This results in a broad Gaussian absorption profile. Because different velocity classes resonate at different frequency, the absorption line of a single transition gets broadened into a Gaussian profile. And the width of this Gaussian profile can range from 500 to 600 megahertz. This is much larger than the natural line width, which is only around 6 megahertz, and the hyperfine splittings. As a result, all the individual hyperfine lines overlap, and we see one smooth, broad absorption dip instead of many narrow ones. So, how do we overcome this Doppler broadening? To reveal the fine and hyperfine structure hidden inside the Doppler broadened profile, we use saturated absorption spectroscopy. The basic idea behind that is two counter-propagating beams. We send two beams from the same laser because we need the exact same frequency through the rubidium cell. One strong pump beam and one weak probe beam. The pump beam should be around 10 times stronger than the probe beam. The key point, the one that you need to understand and that you need to remember, is that they propagate in opposite directions along the same axis at exactly the same path. Here you can see the laser coming through, going through the rubidium vapor cell. This is now the pump laser, hitting the mirror here and getting reflected back into the rubidium cell as now the probe beam and not the pump beam anymore. So now the probe beam goes back into this mirror, gets reflected and into the photodiode. You can see we have exactly the same axis here, so they pretty much overlap the lasers. This is very important. Why do we need those counter-propagating beams? Why do they select zero velocity atoms? Well, consider atoms with velocity v along the beam direction. The pump beam sees them with one effective frequency, while the probe beam, going in the opposite direction, sees them in another. For almost all velocities which are not zero, these two frequencies are different. So the pump beam and probe beam interact with different velocity classes of atoms. However, for atoms with zero velocity, we have that the frequency that the atom sees for the pump beam is exactly the same as the one it sees for the probe beam. These atoms see both beams at exactly the same frequency. This is the crucial point of saturated absorption. When the laser frequency is now tuned to a real atomic resonance for atoms with a velocity of zero, the strong pump beam excites these atoms and saturates the transition. That means that many of them are in the excited state and cannot absorb another photon easily. The weak probe beam passes through the same group of atoms, through the opposite direction. Because they are saturated by the pump beam, they absorb less of the probe light. This produces a narrow increase in the probe transmission exactly at the resonance frequency. In the transmission signal, this appears as narrow Doppler-free features called lamp dips on top of the broad Doppler background. You can see it here. In those Doppler broadened dips, you have some of those peaks. Those peaks are exactly the hyperfine peaks, or as we call them, lamp dips. The broad Doppler profile comes from all velocity classes, but the narrow lamp dip comes only from atoms with zero velocity, which do not experience a Doppler shift. Therefore, the width of the lamp dip is determined not by the thermal velocity distribution, but by the natural line width of the transition, the laser line width, and the finite interaction time. This results in a line width on the order of a few megahertz, which is essentially Doppler free, or let's say this is by far good enough for us. So now let's talk about the final spectrum. Each allowed hyperfine transition, F transitions to F prime, has its own resonance frequency. For each of those transitions, we get a lamp dip in the saturated absorption spectrum. So in the final Doppler-free spectrum, we can see multiple narrow peaks corresponding to the hyperfine transitions of rubidium 85, multiple narrow peaks corresponding to the hyperfine transition of rubidium 87. In addition, we often observe crossover resonances. I will not talk about crossover resonances in detail here. There's enough good information out there. I will just quickly talk about it. So, if two real transitions occur at frequencies omega 1 and omega 2, then atoms with a certain non zero velocity can see the pump resonant with omega 1 and the probe beam resonant with omega 2 at the same laser frequency. This happens when the laser frequency is tuned to omega 1 plus omega 2 divided by 2, so exactly in the middle of the two real frequencies. This produces extra peaks, exactly midway between two real hyperfine lines. I really hope this video was helpful to some of you, and if you have any questions, feel free to put them in the comments and I will try to answer them as quickly as I can. See you hopefully in the next video.